this video, we're going to look at exponential functions. So we will learn to graph exponential functions. We will look at equations where the x and the y are interchanged in the exponential functions. And look at some of the applications of exponential functions. So the first thing is just talk about what an exponential function is and how we make sense of it. Okay? So we have looked at exponential expressions that have rational number exponents, like 7 to the 2/3 or 6 to the 1/4 or something like that. But what about we use irrational exponents? Well, to give it some kind of context, we will make a rational approximation of r. Okay, and you know how to do that. Take the square root of 2 on your calculator, and the number it spits back is just a rational approximation. It's rounded at some point, in other words. So, as r gets closer and closer to the actual value of the square root of 2, which again we don't know, but as we bring it out another decimal place and another decimal place and kind of sandwich r in there between two decimals, we're getting closer and closer to a good approximation of 7 to the square root of 2. We're basically taking 7 and raising it to these two numbers. Okay? So any irrational exponent can be interpreted this way. In other words, by getting closer and closer to a good rational approximation of the exponent. And when we have negative exponents, we're just going to use reciprocals like we always do. That's what negative exponents always mean. We'll bring them up every time we teach you something with exponents, just to remind you, but it always means the same thing. If it's up, goes down. If it's down, goes up. Okay, so we have this function, f of x equals a to the x. A is a positive constant like 7 in the last example. It can't be 1, and x is a real number. So it could be irrational. It could be 7 to the square root of 2. And we call that an exponential function with base a. So to graph one, we can make a table of values like we've done before. And we'll see those dots, and we'll kind of connect them into this line. And we've got this line, this curve. Okay? And after you've done a couple of these by hand, do the one on your calculator, and you can get a better view of them. But I want you to get used to, in everything that you graph it by hand first, just to get a feel for it. So notice how it comes really close to the x-axis, but it doesn't cross it. That means that the x-axis is an asymptote for this function. It will never cross the x-axis, but it will get closer with every negative number. And you see here you've got 1/3, 1/9, the next is going to be 1/27, 1/81. So you'll get closer and closer, but you'll never actually touch it. And let's graph this one. The last one we had was 3 to the x, and this is 1/3 to the x. And let's look and see what happens. Looks exactly the same, except it's going the other way. The value you had for -1 in the previous example, you now have for +1. And it's because of the reciprocal of the negative exponent. Because remember, x is the exponent here. So it's what we call a reflection of y equals 3 to the x. If this y-axis acted like a mirror, you flip one across that axis, and you'll get the other curve, either one. So they are reflections of each other. And that's a term you'll get into a lot more in pre-calculus, but I just want to introduce that now. So, here are the observations we can make. When you have a base, a, that's greater than 1, your graph is going to increase from left to right. In other words, it's going to get asymptotically close to the x-axis as the numbers get more negative, and it's going to get really, really big as the numbers get more positive. But if you have a fraction for a base, or anything between 0 and 1, the graph of it is going to decrease from left to right. So the small values will be as the x values get bigger. That's where it'll get asymptotically close to the x-axis. And on the left is where the numbers will go really, really high. All of them, every single one of them, goes through the point 0, 1. Because anything raised to the 0 power, any a raised to the 0 power will give you 1. So all of these graphs have the x-axis as the asymptote. When a is greater than 0, when that base is greater than 0 and not 1, the domain of f is all real numbers, and the range of f is all positive real numbers. It's only the positive real numbers because, again, it's getting asymptotically close to the x-axis. It will never reach 0, but it'll get darn close. Okay? I leave it to you to figure out why a can't be 1. Just think for a minute and you'll figure it out. If a is greater than 0 and a is not equal to 1, the function is 1 to 1. In other words, it passes the horizontal line test, and it's a function, so it passes the vertical line test. So every member of the domain has one and only one member of the range associated with it, and every member of the range has one and only one member of the domain associated with it. Now, sometimes you're going to want to exchange the y and the x, and it will be helpful to be able to graph an equation where it is like x equals a to the y. So x equals 3 to the y. Again, we will make a table of values for it, and we'll draw it out like that, and you see what happens? It's just turned 90 degrees. So now it's the y-axis that's the asymptote. And it goes through the point 1, 0 instead of 0, 1. So it's never going to cross or touch the y-axis. So what applications would you possibly use this for? Big deal with interest, compounded annually. In fact, almost, I would say all of the finance formulas that you would learn in Math 107 or that are commonly used have exponential functions in them. So it's really helpful to know how to work with these. So if you compound interest annually, so every year you get a certain amount of interest, say 5% interest on $100. If your interest rate is I, after t years, here's how much money you'll have. Here's the formula for it. Notice it's an exponential function. So let's just apply that. We have $60,000 invested at 5% interest and it's compounded annually. So let's find the function where it's t years, and then we'll plug in for t and see how much money there is after 6 years. So if we just put in the interest rate I, 0.05, and the principal, 60,000, into that original equation that we're given, we end up with this. Okay, that's the function for the amount after t years. And if we simplify it down, this is what we get. Now, if we put in the 6 for the t to find out how much we get after 6 years, and we plug this all in our calculator, we will get, rounded to the nearest cent, $80,405.74. Compounded annually, if you don't know what that term means, it means that each year they'll take 5% of the principal and add that to the principal. And then for the next year, your new principal is that whole amount. So they'll take 5% of that whole amount. So they keep taking an extra 5% of the 5% they added every year. So that's why it adds up quicker. And if it's compounded monthly or compounded weekly or compounded daily or continuously compounded, then you get different results because there's more and more money that you're taking that 5% of each time. So that's a really good example of how we use exponential functions. We also use them in growth functions, growth of populations and things like that.